Ladies and gentlemen, welcome to this lecture on charging electric vehicles from renewable energy sources. The following topics will be introduced in this lecture. First, why do you need to charge electric vehicles from renewable sources of energy? Second, what power converters needed for charging electric cars from photovoltaics and from wind? And finally, how can we implement smart charging of electric vehicles from renewable energy sources? The main driver for moving to electric vehicles is because they have no tailpipe emissions and they are more efficient than combustion engine cars. However, if the electric vehicles are only sustainable if the electricity used to charge them comes from renewable sources of energy and not from fossil fuels. In this graph, we see the equivalent carbon dioxide emissions from a life cycle assessment, which includes the emissions due to vehicle production, the well-to-wheel emissions for the fuel, the vehicle maintenance, and the end-of-life recycling of the vehicle. The emissions for different combustion engine cars are shown on the right side, while the left side shows the emissions for battery electric cars charged from different electricity generation mix. We can clearly see that electric vehicles have far lower emissions from a life cycle perspective, even when charged from an electricity grid dominated by fossil fuels. However, if the electricity itself is generated from non-emitting sources like wind, hydro, or nuclear, then the life cycle emissions of the electric vehicles are further lowered and the well-to-tank emissions even become zero. It is hence necessary to use renewable source of electricity to charge electric cars in the future to make them truly sustainable. Now, let us look at how we can develop an EV charging system powered by wind and solar energy. Let us first start with wind energy. In case of wind energy, three key factors play a role in the design of the charging system. First, wind power is typically generated today using onshore and offshore wind farms that are located far away from where the electric vehicles are charged. This means that the power must be transported long distance between the supply and the electric vehicle load. Second, a wind turbine is typically rated in the order of megawatts, while EV charger is normally working in the order of kilowatts. This shows a big difference in the power scales and the potential of one wind turbine to charge several hundred vehicles. Finally, wind generation is maximum in winter and in the night time. Hence, wind generation is ideally suited for charging electric cars at the homes in the night. From a power conversion perspective, generators used in wind turbines typically produce variable frequency AC power. Two back-to-back AC to DC converters and DC to AC power converter are used to convert the variable frequency AC power to high voltage or medium voltage 50 Hz or 60 Hz AC power used for long distance power transmission. This power is then stepped down to low voltage AC power, and the electric vehicle can then be charged using either AC charging or DC charging. On the other hand, things are a bit different when charging electric vehicles from solar energy. First, solar panels have the benefit that they can be installed on the rooftop of buildings besides just being installed as solar farms. Therefore, solar power can be generated close to where the electric vehicles will be charged, thus reducing the transmission losses. Second, rooftop solar PV systems are typically rated in the same order of kilowatts, which is similar to the power rating of an electric vehicle charger. Finally, in contrast to wind generation, solar generation is maximum in the daytime and in summer. Hence, solar generation is ideally suited for charging cars at the workplaces during the day. The simplest way to realize a solar-powered EV charging station is to use a solar photovoltaic inverter. Inside the inverter, a DC to DC power converter operates the solar panels at the maximum power point. Then, a DC to AC inverter converts the direct current or DC power to 50 Hz or 60 Hz AC power for AC charging of the electric vehicle. There is, however, one disadvantage with this method. Photovoltaic panels and the electric vehicle battery are both fundamentally direct current or DC by nature. And in this method, we convert the DC power for the photovoltaic panels to AC, and then we convert the AC power back to DC for charging the car. That means there is unnecessary power conversion in this method. Hence, a more efficient way to charge electric vehicles from photovoltaics is to use an isolated DC to DC converter and directly charge the electric vehicles from the photovoltaic using DC charging. Let us look at an example on how to do this. At the Delft University of Technology, together with our partners PRE and LMS, a 10 kilowatt solar power DC charger has been developed. It has 3 power converters inside: a DC to DC converter for the solar panels, a DC to DC isolated converter for the electric car, and a DC to AC inverter to connect to the AC grid. Using this design, direct DC charging of the EV from the photovoltaic panels can be realized. Secondly, if there is no electric car, then the system acts like a solar inverter and directly feeds the PV power back to the grid. Third, if there is no solar power, the system operates as a conventional DC charger and charges the EV from the grid. Finally, the charger is bidirectional and it's capable of vehicle to grid. So the electric vehicle can not only charge from the grid, but it can also send the power back to the grid as well. The unique aspect of combining solar charging and vehicle to grid is that the electric car battery can now be used as a storage for renewable electricity. Now imagine a scenario where you can charge your car at the workplace using solar energy, and you can drive back to your home and power your home in the evening using vehicle to grid. Of course, the main challenge with powering electric cars from renewable energy is the variability in the generation. Let us take an example. In this graph, we can see the daily energy yield of a 10 kilowatt PV system in the Netherlands for 1 year, showing the seasonal variation in the generation. We can see maximum generation in summer and minimal generation in winter. It is also interesting to note that the daily yield can range anywhere between 1 kilowatt hour all the way to 75 kilowatt hour over the year. What this means for electric vehicle charging system in the Netherlands as powered by solar is that you can charge less than half of a 30 kilowatt hour battery of a Nissan Leaf car in winter, about 1 Leaf car in spring, and about 2 Leaf cars in summer. Bear in mind that depending on the location and weather condition, the situation can be much better or worse than this. Either way, there will always be seasonal and daily variations in the generation which has to be considered. Wind generation, on the other hand, has the opposite behavior. In this graph, we can see an inverted U variation in the average wind power for the Netherlands over the year, where there's more generation in winter and less generation in summer. Now, how do you overcome this variation in renewable energy? A possible solution is to overcome this variation is to size the wind and solar installation such that we are guaranteed of sufficient energy even when the sunshine and wind are minimal. The disadvantage of this is that there will be overproduction and wastage of power when the solar installation and wind speeds are at their maximum. For example, in this graph, we see the fraction of total renewable energy lost when different combinations of wind and solar are installed for powering a network. The left side corresponds to a scenario with 100% wind generation, and the right side corresponds to 100% solar generation. What this graph shows us is that the key to reducing the energy lost is to install an optimal combination of both wind and solar energy so that the day and night variation and the summer winter differences in power production between the wind and solar can balance each other. A second solution to help match renewable generation and the electric vehicle charging is smart charging. When solar and wind generation are high, the EV charging power can also be increased, and vice versa, the charging power can be decreased when the renewable generation is low. This has the dual benefit of making electric vehicles sustainable by using more green energy and reducing the stress on the grid due to large-scale renewable energy generation. In case of AC charging, if you want to implement this smart charging, the pulse width modulation signal on the control pilot of the Type 1 and Type 2 AC chargers can be continuously controlled to adjust the EV charging current based on the solar or wind generation. For CHAdeMO and Combo DC charging, the CAN bus and PLC communication can be respectively adjusted so as to change the charging power based on the solar generation. So, to wrap up this lecture, in this lecture we looked at why electric cars in the future must be charged from sustainable sources of electricity like wind and solar. We looked at the power conversion required for solar and wind-based EV charging systems. And we looked at two methods that can be used to overcome the variability in renewable energy generation. One is to use an optimal combination of wind and solar energy so that they can help balance each other's variation. And the other technique is to use smart charging of electric vehicles based on renewable energy generation. Thank you.